Assalamualaikum warahmatullahi wabarakatuh. Nama saya Muhammad Ikmal bin MUDA. So, hari ini saya akan terangkan tentang lab 2, iaitu Process Control Laboratory, iaitu on-off and proportional integral derivative and PID controller. So, first, we construct the block diagram for on-off controller. So this is our desired output block, which is have a desired temperature, on-off controller, transfer function, initial temperature, sum, scope, and sim out. So for the first one, we have to set up the parameter for the desired temperature. We set a sample time. We set a final value to the 85. So we okay, so next we go to the model configuration parameter. For the model configuration parameter, we set the simulation time, which is a start time from 0 until stop time to 5000. Solver option, we choose a type of solver, which is a ODE 45 dormant prints, and we set a max step size 1, minimum step size 0.99, and initial step size is 0.99. So we click OK. So after that, for the experiment procedure, we for the block diagram of on-off controller, we for the switch off point, we change to 3 and -3. So these are for the switch on point and off point. If it is a on-off controller neutral zone, and for the output is a control signal. So we click apply and OK. So after that, we run the simulation. Graph for the -3 and 3. So after that, we change the to the 1 and -1. So we click apply and OK. We run. So we get the output from this scope. So this is the output from -1 and 1. So after that, we set the on-off controller to 6 and -6. Apply and OK. So this is our graph scope for -6.
Assalamualaikum warahmatullahi wabarakatuh. So for my part, I will explain about the part A, which is the P controller. So the first step that we need to do is to set the KI, which is the integral gain, and KD, derivative gain, to zero value. So I've been set this up before, and for the KP, which is proportional gain, uh, the value is 0.0024. So after that, after doing all this block diagram and also set the gain value, we need to run it first. It might take sometimes, so let's just get patiently. Okay, and then double click on the scope icon to see the output. So this is the waveform of P controller. As we can see that it doesn't reach the offset value, which is 60, but the system still in stable mode because there is a little oscillate. There is only a little bit oscillate here. So for the next step, I need to change the value of KP, which is the proportional gain, to 0.0.0.00009. Run it, then double click on this scope. You see there is no overshoot value right here, but it's still in stable mode, which is the controller is stable. And last but not least, we change it to value 0.005. Let's see how does the waveforms looks like. So this is the waveform, and it's oscillate and didn't maintain on the didn't have the straight line, which is didn't maintain. So in my opinion, the value, if the value of KP, which is the proportional gain, is 0.0009, the the system will be more stable. Thank you. Assalamualaikum warahmatullahi wabarakatuh. So for lab 2 MKS, I will be presenting for part B, which is the PI controller and also the PID controller. So first of all, we need to set the KD value to 0. As you can see that I've been set up this just before the presentation. And the integral gain, which is Ki and Kp, to the value that has been taught in the lab sheet, which is the Kp is 0.00216. So after all the process have been done, we need to run it. And then wait a second. And then we just click on the scope icon. So this is the graph. This is the um, offset value, and this is the overshoot value, and this is the time that the system, the controller, take to maintain the to stabilize. So after that, we need to change the value of ki, which is 0.0000632. So let's do it. Okay, then run it. Compiling, and then double click on this code. Okay, so you can see the difference uh, between the previous waveform is this graph oscillate a little bit more, and then it takes time to stabilize. And for the last one, for the PI controller, we need to set it to 0.0000222. This is it. Run, and then double click this code. As you can see, it oscillate less than the second value, which is 0.632, but it also needs time to stabilize. So in my opinion, the first waveform, which is the 0.00216, is more stable.
Assalamualaikum and greetings. My name is Muhammad FAHMI, and I will continue to demonstrate for part C of a PID controller. So we need to set the proportional gain KP, integral gain, and derivative gain of PID controller by double click the block of the proportional gain, and then we set the gain parameter for the all three blocks. So for the proportional gain is 0.0029, and for integral gain is 0.0000096, and these two gain will be fixed variable, and the manipulated variable will be a derivative gain. Is for the first value, we need to set to 0.2175. Then we run the simulation. So this is the first signal for the 0.2175 derivative gain. And then we repeat the step, and we change the value of derivative gain to 0.5. So we will obtain the second output signal for the second value parameter, and lastly is for 0.0575. And lastly, this is our graph for derivative gain value. And that's all from. For the last experiment, which is a PID controller tuning to adjust the proportional gain, integral gain, or derivative gain of the PID controller in procedure 5.33. To achieve the following requirement of the system, which is 2% by setting time must be less than 2700 seconds, and percentages overshoot must be less than 30%. So for the system, we set the proportional value to 0.003, integral value to 0.0000006, and derivative gain is at 0.03 value. And then after we run the simulation, this is our scope. And the settling time we can measure from the cursor is 1.786 kilosecond, which is 1786 second, and the maximum overshoot is at 62.5 minus by 60 and then divided by another 60, and then we will get the percentages overshoot of the system is 4.16%. And that's all from me. Thank you.